Hi everyone. So I hope the test went okay. So the next section, I believe, is 2.2 in the book, and we're going to start finding derivatives, but not using the definition anymore, right? So this is the definition that you had to use on the first test, and we know what a pain this is to have to use this, and in most cases. In some cases it might not be that bad, but yeah, for most of them, using the definition to find the derivative is not pleasant. In some cases it's just extremely tedious, and in a lot of cases it's just impossible. So we just have to develop a bunch of rules that will help us take the derivative without having to use this definition anymore. All right. And so we're just kind of building up our rules for derivatives, just as we did for limits. Just keep in mind that even though the derivative, right, is a limit here, some of the rules that have to do with derivatives are not necessarily going to be the same as they were for limits. So just keep that in mind. So let's just start with our first rule. And maybe I'll label it as it is in the book. This is theorem 2.2. But this is really just if you're taking the derivative of a constant. Right? So here, let's let C, and later we'll use K, be real numbers, right? So that means constants. Numbers or constants. Okay. Oh, and actually before we do this rule here, let's just get used to some notation. So we already know that the derivative, okay, so I'll do it here, right? So the derivative of a function, say y equals f of x, we can represent that in two different ways. We can represent it as dy over dx or f prime of x. And we're going to go back and forth, so you got to get used to both. But I'm going to use this notation for the time being. And in fact, what we're going to say is, right, the derivative of y, we can think of this as the derivative of y, right? Which is also, because y is f of x, it's the derivative of f of x. And we can also write that as f prime of x for short, right? So yes, this symbol here, right, d over dx means take the derivative of whatever comes after it, right? So if this is, let's say this is a, this just means I want to take the derivative of a with respect to x. Okay, so with that, now we can go back to theorem 2.2. So let's just do that down here. Okay, so we want to take the derivative of c. Right? What's the derivative of a constant? Well, remember that the derivative represents the rate of change of a function. Right? So if c is a constant, well, it's not changing, right? It's constant. A constant is a number. Numbers don't change, right? So the derivative of a constant would be 0. Okay? Right? So, right, if you want to take the derivative of any number, 17, the derivative of that is 0. Right? The derivative of pi, right? Pi is a number, is 0, and so on. Okay? So that's if you have a constant. The next thing we're going to do is take the derivative, so this is theorem 2.3, the derivative of x to any power, right? So x to the n, well, for n being an integer. So n is an integer, Right? So it could be positive, negative, right? So -3, -2, -1, 0, 1, 2, 3, and so on. Although it will apply to all real numbers, but for now, let's just say it's for integers. So the derivative of x to the n, and I'm, without going through y here, I'll just say what the derivative is. It's going to be n times x to the power n minus 1. Okay, so this is called the power rule, and this is one you should learn very quickly because we are going to use it over and over again. So very important rule here. Right. Yeah, so let me forget the fact that this is an integer, right? This applies to any all real numbers, right? So for n, say any real number. So it doesn't have to be just the integer. So the book proves it only for integers. We can prove it for real numbers, but we'll do that in chapter 5. Okay. So this is the power rule. So some examples. If you take the derivative of x squared, so here n is 2, well, if n is 2, this is going to be 2 times x to the power 2 minus 1. But 2 minus 1 is 1, and x to the 1 is just x. So we get that the derivative of x squared is 2x. And yeah, I think this was done probably in the book in 2.1, where they use the definition, the limit definition, right? I remember doing x cubed in the last video, and yeah, remember how long that took. But now, if you understand the power rule, it just goes like this, right? Bring the 3 in front and decrease the exponent by 1, right? So 3 minus 1 is 2, and we get 3x squared. So look how much faster that is. And now, if you're asking, why didn't we learn this in the first place? Why did we have to learn this, the definition? Well, sorry about that. Well, you have to know what it is. You have to know what it means before you can learn the rules, right? Same thing with limits, right? We didn't learn the rules for limits and then say, oh, well then what is a limit, right? We learned what is a limit first, and then we learned the rules. So same thing here, right? Now let's do a few more. Let's make them a little bit harder. How about the derivative of the square root of x? Right. And this is one I think we also did in the last video. Again, using the definition. But here we're going to use the power rule. Now, hopefully you remember that the square root of x is also x to the power 1/2. So here n is 1/2, right? Remember, n does not have to be an integer. It can be a fraction or a decimal or any real number, right? So, yep, applying to n is 1/2, we get 1/2 times x to the power 1/2 minus 1. Well, what's 1/2 minus 1? It's negative 1/2. So we get 1/2 x to the negative 1/2, or if you prefer, in terms of a radical, remember negative 1/2 means it's in the denominator, right? So this is 1 over 2 times x to the positive 1/2. But then x to the 1/2 is also the square root of x. So this is just 1 over 2 square root of x. And that's the same thing we got by using the rule, except that we had to do the little trick of using the conjugate and all that. This, I think, is much easier, right? Yeah, let's do a few more. Let's do, let's do the one I did in the video. Let's do 1 over x squared, right? So I distinctly remember, excuse me, doing this the long way, right, using the limit definition way up here. And it took, well, several minutes. It probably took, I don't remember, maybe close to 10 minutes when all was said and done, to do this. But now that we know the power rule, well, remember this is a fraction, but 1 over x squared is the same as x to the negative 2. So now our n, back to the power rule here, is negative 2. So bring the negative 2 in front, and then decrease the exponent by 1. So negative 2 minus 1, right? Be careful, it's negative 3, right? So this is going to be negative 2 over x cubed. And that was what we got using the definition. What took 10 minutes, maybe? Didn't even take 1 minute, right? Well, okay, maybe 1 minute, 45 seconds, 1 minute, whatever. So you get the idea, right? The exponent can be positive, negative, it can be fractions, it can be decimals, it can even be, pi. So if you're taking the derivative of x to the pi, well, here n is pi, so n times x to the n minus 1 is pi times x to the power, pi minus 1. And I don't think we're going to be able to simplify that, so in this case, that's the answer. Kind of boring, but that's what it is, right? So you get the idea, right? You can use this for any exponent, right? I mean, we could even do it for n is equal to 1, right? The derivative of x to the 1 is just 1 times x to the 1 minus 1. But 1 minus 1 is 0, and x to the 0 is not 0, it's 1. And 1 times 1 is 1. Yeah, of course, that's one that you should know already from the definition, that dx over dx is just 1. After all, you can think of these as just canceling, but well, maybe not the best way to think of it, but it does work if you want to do it that way, right? Okay, and there's plenty more examples in the book, but this is an important rule, power rule, so make sure you know that. But we have some more rules to learn, so let's get to those. Theorem 2.4. So this is if we have not a constant, but a constant times another function. Right. So in other words, we want to take the derivative of, let's say, c times a function f of x. So remember, the derivative of c itself is 0, but c times f of x now depends on x, right? So it turns out that the c can just come outside the derivative. You multiply c times the derivative of f. So f prime of x. Okay. Very useful. And, I mean, okay, so I'm not going to show this. It's actually a very quick proof using the definition. Rather than do that, let's just do some examples. So, for example, suppose, well, let's write it this way. Suppose y is equal to 8x cubed. We want to find the derivative of y. Well, right, so we're going to we still have to take the derivative of 8x cubed. Now the 8, right, that's my c, that's my constant. And according to this rule, I can take the constant outside. I think I have enough space to do that here. So multiply 8 times the derivative of x cubed. Right? So yeah, this 8 is a constant. It can come outside the derivative, right? Makes sense? That's what the rule says you can do here. Now, we still have to take the derivative of x cubed. But we did that already. That was like the second one we did. It's 3x squared, right? So, just multiply 8 times 3x squared. And 8 times 3 is 24, so 24x squared. That's it. That's the derivative of 8x cubed. Okay. Let's do a few more. So I'll just write it this way. Suppose we want to take the derivative with respect to t, this time, of negative 6 t to the negative 3. Okay, so the negative 6 is a constant. That can come outside the derivative and multiply the derivative of t to the negative 3. So, of course, you could write this as 1 over t cubed, but it's more convenient to leave it as t to the negative 3 so that we can use the power rule, right? We did x to the positive 3, so what would x to the negative 3 be? Again, don't forget the negative 6 in front. So bring the negative 3 in front, and then decrease the exponent by 1, right? Negative 3 minus 1 is not negative 2, right? Take away 3, take away 1, you took away 4. So it's going to be t to the negative 4. And then negative 6 times negative 3 is positive 18. So we get 18t to the negative 4, which you can also write as 18 over t to the positive 4. And you should know that, but I'm not picky. I'll accept it either way, right? Yeah, I guess let's go back to x, take the derivative of 4 over 3 squared of x. So how do we do that? Well, before we take the derivative, let's just rewrite this a little bit. The 4 over 3 is what multiplies the 1 over squared of x. Right, so the 4 over 3 is the constant. So that will bring in front, but not just yet. Before we do that, what's 1 over squared of x? Right. We saw that earlier, right? When we did 1 over squared of x is x to the negative 1/2, right? So this is going to be 4/3 times x to the negative 1/2. The negative because it's in the denominator, and then the 1/2 because it's the square root. Okay, so I know I'm getting a little bit cluttered here. Let me see if I can do this down here now. So, okay, so the 4 over 3, that's the constant. That can come in front. And now we just take the derivative of x to the negative 1/2. So we bring the negative 1/2 in front, and then we decrease the exponent by 1. So negative 1/2 minus 1. Right, so I hope you can do that in your head. It's negative 3 over 2. Right, get a common denominator. Negative 1 over 2 minus 2 over 2 is negative 3 over 2, right? And then what goes in front? So it's a positive times a negative, which is negative 4 over 6 reduces to 2 over 3. So we get negative 2/3 x to the negative 3/2. Or if you prefer, you can do negative 2 over 3 times x times the square root of x. And I'll leave it to you to figure out how to go from one to the other. But you should know both of these, right? Again, I'm not picky. I would accept either, right? So from now on, negative exponents, not an issue, not a problem. But you should know how to simplify those. Okay. So that's what you have when you have a constant times a function. Even if that constant is a fraction like 4 over 3, right? Could be any real number. Could be your c here, right? So I hope that helps. So let's move on to the next rule. And I think I'm just going to clear this and start all over. Okay, great. Okay, so this is theorem 2.5. And there's a name for this. This is the sum rule. It's what you want to do if you want to take the derivative of the sum of two functions, say f of x plus g of x. Well, it worked for limits. That doesn't mean it works for derivatives, but luckily it does. In other words, it's exactly what you would expect to do, right? The derivative of the sum of two functions is just going to be the sum of the two derivatives. And we can write this more succinctly as f prime of x plus g prime of x. So the sum of the derivative of the sum is the sum of the derivatives. Okay. Again, why that works goes back to the definition. If you want to do the limit definition, go right ahead. But this should at least make some sense in terms of the limit of a sum is the sum of the limits, right? Okay. Another way to write this, by the way, is if, let's say, we have two quantities, u and v, the derivative of u plus v is just the derivative of u plus the derivative of v. So that's if your f and g are just variables like u and v. So either way. Okay, some examples. Well, let's just start with the derivative of, how about x to the 5 plus x to the 4. Well, right, so we can think of my u as x to the 5, my v as x to the 4. And so you just take the derivative of x to the 5 plus the derivative of x to the 4. And for each of these, just use the power rule, right? So the derivative of x to the 5 is 5x to the 4, and the derivative of 4 is 4x to the 3. And that's it, we're done. Right? Again, way easier than using the limit definition. Right? Let's do another one. How about if we want to take the derivative, let's go back to t now, of how about t to the 3 plus 2t to the negative 3. Okay, so, well, we take the derivative of t to the 3 plus the derivative of 2t to the negative 3. Okay, so for the first one, we did this several times already, right? So 3t squared, just by the power rule. Now for the second one, there's this 2 in front, but the 2 is a constant. That can come outside. And then we take the derivative of t to the negative 3. Right? So be careful. Don't take the derivative of this. We already did that, right? There's no d over dt in front. So this is already part of the answer. Where we still have the d over dt, that means we still need to take the derivative. So now we apply the power rule for n is equal to negative 3. So that's going to be negative 3t to the negative 4. Right? So 3t squared, and then 2 times negative 3 is negative 6, t to the negative 4. And we can just leave it at that. Okay. Let's do another one. So this sum rule can be used for basically any polynomial here. So let's write it this way. How about r is equal to 5x, let's do 5x to the 8 plus 2x to the 5th minus 7x squared. Oh, plus 9. Okay, so we want to find the derivative of r with respect to x, or you can also write it as r prime of x. But I'll write it as dr over dx. Okay, well, we have to take the derivative of this whole thing. 5x to the 8 plus 2x to the 5 minus 7x squared plus 9. Now, before we do this, what I should tell you that I'm going to go through this step by step. Okay? Because this is, we're still getting used to these rules here. However, at some point, you should be able to do this all at once, right? I mean, this at some point should be so easy that you can just write down the answer. Okay. So I'm going to do that eventually, but not for this one. Okay, so for this, we have the sum rule. So this is going to be the derivative of 5x to the 8 plus the derivative of 2x to the 5. Oh, and minus. Now, wait a minute. This is the sum rule. It doesn't say that you can do this if you're subtracting. Well, it turns out you can. So if this is a plus or a minus, you can still take the derivative of the difference, right, as the difference of the two derivatives. So this will be plus or minus, right? So in reality, this is a sum rule or a difference rule. So you can use it for sums or differences. Okay? Yeah, so we can just take minus the derivative of 7x squared, and then plus the derivative of 9. Okay. Well, can we take the derivative of 5x to the 8? Sure. Again, the 5 just comes outside, right? So this will be 5 times the derivative of x to the 8. We can do the same thing with the 2 here. The 2 is just a constant. That can come outside. And the 7. 7's a constant. That can come outside. Now, it's going to be negative 1 times 7, so negative 7 times the derivative of x squared, plus, well, what's the derivative of 9? Yeah, 9 is a constant. The derivative of a constant is 0, so the derivative of 9 is 0. Good. All right, now just use the power rule for each of these, right? If n is 8, the derivative of x to the 8 is 8x to the 7. Right? The derivative of x to the 5, 5x to the 4. And the derivative of x squared, 2x to the 1, or just 2x. Right? Plus 0, well, we don't need plus 0, right? And then 5 times 8 is 40, so 40x to the 7. 2 times 5 is 10, so 10x to the 4. And then negative 7 times 2 is negative 14, so negative 14x. And there you go. So, like I said, I went step by step by step here. And for the time being, you should probably do the same, so you don't get too confused trying to do it all at once. However, once you really get used to this, right, if you do this, eventually you'll see that this is something you can probably just do in your head, right? So if you multiply the 8 times the 5, that's where you get the 40 from. And then 8 minus 1 is 7, right? So, and so on. So a lot of this you can do in your head, which means that at some point you should get really used to this, where this is second nature. And then going from, right, the derivative to the answer shouldn't take you more than just a few seconds. Okay. In fact, maybe let's try that, right? Let's do one. Let's just take the derivative of, let's do, I don't know, 12x cubed minus 4x squared plus, let's do 6x to the negative 7. Okay. So how do we do this all at once, right? So remember, the 12 is a constant, and then we just multiply by the derivative of x cubed, which remember was 3x squared. So 12 times 3 is 36 times x squared, right? And negative 4 times 2 is negative 8. And the derivative of x squared is 2x, so x to the 1. 6 times negative 7 is negative 42. And this is where we have to be careful, right? The temptation would be to say negative 7 minus 1 is negative 6. No, that's negative 7 plus 1. Negative 7 minus 1 is negative 8. Okay. So, yeah, if you didn't get that, then go back and do it step by step. But you can see that eventually this should not take you long to do just the derivative of a polynomial. In this case, this is not a polynomial because of the negative exponent, but, you know, not a big deal. It's a rational function, and you could rewrite this as a rational function, but we're not going to do that yet. Okay, one more. Let's take the derivative of, oh, let's write it this way. How about h of x is the cube root of x. I don't think we did that one yet. Plus, how about 1 over the fourth root of x? Okay. And again, the question is to find the derivative of h. Right? Okay, so first of all, this is a sum. Before we take the derivative, however, we might want to write this in terms of exponents, so we can use the power rule, right? So the cube root of x is x to what power? How about 1 over 3, right? If the square root has a power of 1 over 2, the cube root is power 1 over 3. What about 1 over the fourth root of x? Well, it would be 1 over x to the power 1 over 4. But if you're taking the reciprocal of 1 over x to the 4, you get x to the power negative 1/4. Okay, so that's not the answer, right? That's the original function. We haven't taken the derivative yet. All we did was rewrite it so that now it should be easier to take the derivative, right? So now we can take the derivative of x to the 1/3 plus x to the negative 1/4. Okay, so using the sum rule, we just take the derivative of x to the 1/3 plus the derivative of x to the negative 1/4. Got that so far? Now just use the power rule, right? So we bring the 1/3 in front. We multiply by x to the 1/3 minus 1. And then plus, well, we bring the negative 1/4 in front, so that'll end up subtracting. X to the negative 1/4 minus 1. So I'm hoping you can do these little subtractions of fractions in your head. 1/3 minus 1 is negative 2/3. And then we have minus 1/4 times x to the negative 1/4 minus 1 is negative 5 over 4. And you're welcome to leave it like that. Or because this was originally in terms of radicals, if you want to write it as a radical, you can do 1 over 3 times the cube root of x squared minus 1 over 4 times the fourth root of x to the 5th. Actually, I'd be okay with that. But it turns out you can simplify the fourth root of x to the 5th in the following way. Let me make sure that part's right. So it's going to be 1 over 4 times x times the fourth root of x. Okay. And of course, we should also rationalize the denominators, but as you know, in some cases we would rationalize the numerators. So I think having an irrational denominator here is fine. So I'd take any one of these as the correct derivative. Okay, so that's the sum rule. And again, it works if it's a difference as well, right? So whenever you have a difference here, right, you can also just take the derivative of the difference by taking the difference of the two derivatives. Okay. Oh, out of space, so let's start over. Okay, on to the next rule. So this, again, in the book is theorem 2.6. And we're going to do the trig functions now. We're going to take the derivative of the sine function, sine of x, and we're going to take the derivative of the cosine of x. Cosine of x. Now, what about tangent, secant, cosecant? We'll get to those later. We're not going to be able to do those just yet. But we can do one of these. And I think I'm going to show you how to do this one here. This one is in the book. The sine is in the book, I think. It's an example in the book. But I think cosine is probably one of the homework problems. So if it is, then it's a freebie. But let's take the derivative of cosine of x. So what's the rule for the derivative of cosine x? Well, some of you probably know it already. Great. But if you don't know it, then how do we get it? Yeah, see, this is why you have to know the definition of the derivative, because the only way that I know how to get this rule is to use the limit definition. So we're going to use the limit definition again. I'm going to change the delta x to h. So we're going to use h goes to 0 instead of the delta x. It's just easier, I think. So here it is. This is going to be the limit as h goes to 0 of cosine of x plus h minus the cosine of x all over h. Okay, so that's just using the definition. Right, h goes to 0. Now what? Well, now most people would get stuck here, I think, because how do you simplify this? Cosine of x plus h minus the cosine of x. So this is a trigonometric identity, and I'm going to go way down here to remind you of the cosine of a plus b. Okay, so this is one that you may or may not remember from your trigonometry days, but it is an important rule here. Cosine of a plus b is the cosine of a times the cosine of b minus, oops, sorry, see, even I forget sometimes, right? Minus the sine of a times the sine of b. Okay. So yeah, ideally, look, you should know this. But if you don't, look it up in the book. It's in the front cover. Oh, if you have the hardcover edition, it's in the front. Right, so look it up in the book. If you have the e-book, it's in probably the very beginning. Right. So yeah, you can, obviously, you know that the tests are open book. So if you ever come across something that doesn't look familiar, see if you can find it as one of the formulas in the book. This is one in the book, right? So we're going to use this up here now, where I'm going to replace x. I'm going to replace a with x, right, and b with h. So, right, cosine of x plus h will be cosine of x times the cosine of h, right, times, and then minus, sorry, not the cosine, I did it again, right, sine of x times the sine of h. Right. And then we still have minus cosine of x, right, all over h. So how does that help? Well, it doesn't look like it helps much, right? It doesn't look like we can do a whole lot here. So here's what I'm going to do. I'm going to switch these two terms. You can always change the order, right? Cosine of x times cosine of h, and then minus the cosine of x, and then minus the sine of x times the sine of h, right? So you can always change the order of the terms, right? 1 plus 2 is 2 plus 1, and so on. Okay. Now what? Well, notice in the first two terms here, right? Just in these two terms here, I have a common factor of cosine of x. This is cosine of x times 1. So I'm going to factor out the cosine of x and multiply cosine of h minus 1. Right? And this is a product. I can't really factor anything out here. I can just write it as sine of x times sine of h. Okay. But look, this is a difference, right? The limit of the difference is the difference of the two limits. So I can write this now as limit as h goes to 0 of cosine of x times cosine of h, sorry, not hyperbolic cosine, cosine of h minus 1 over h, and then minus the limit as h goes to 0 of sine of x times sine of h over h, right? Okay, now keep in mind that the variable here is not x, it's h, right? We're taking the limit as h goes to 0, which means the cosine of x is independent of h. The cosine of x is like a constant. Same thing with the sine of x. So I can pull those outside the limits because they don't depend on h, right? So this is now the cosine of x times the limit as h goes to 0 of cosine of h minus 1 over h. And then minus, we have the sine of x times, right, the limit as h goes to 0 of sine of h over h. This is looking a lot better, right? In particular, you should know these limits already. We did them back in chapter 1. So I hope you're thinking about that. Yep. So I think this was 1 minus the cosine of h, but then you just get the opposite, right? So the limit as h goes to 0 of 1 minus cosine h over h was 0. So if you reverse it, cosine of h minus 1, you get negative 0. But negative 0 and is just 0, right? So yeah, that limit is 0. So what's the limit as h goes to 0 of sine h over h? That limit is 1, right? It's not 0 over 0. It's just 1, right? So anything times 0 is 0. So 0 minus sine of x times 1. This is just negative sine of x. And that's the derivative. So going back up here, the derivative of cosine of x, oh, sorry, I put a box around it here. I didn't mean to do that, messing that up, is just negative sine of x. This makes for a terrible eraser, by the way. Sorry about that. Okay, so yeah, the answer here is minus sine of x. Okay, so unless you want to go through all this again, and I know you don't, this is one you better remember because it will come up again and again and again. Now, having done that, we know what the a and the b were here, right? Having done that, we're not gonna do this all over for sine of x. So here's the answer. The derivative of sine of x is cosine of x, right? Positive cosine x. So the derivative of sine is cosine. The derivative of cosine is negative sine. So make sure you know those. And again, we can do a couple examples here. Suppose y is equal to 36 times the sine of x minus 47 times the cosine of x. We want to find the derivative of y. Okay, so what's dy over dx? Well, this just means we have to take the derivative of 36 times sine x minus 47, that's supposed to be 4, times cosine of x. Well, I'm going to do two rules at once here. This is the difference rule and the constant times function rule. So pull out the 36, then take the derivative of sine, right, minus 47 times the derivative of cosine. Sorry, it's supposed to be a C. Well, 36 times the derivative of sine is cosine. Minus 47 times the derivative of cosine, don't forget the negative sine of x. So this is just 36 times the cosine of x, and then negative 47 times negative sine x is positive 47 times sine x. So 36 cosine x plus 47 sine x. Okay. And I think that's it for the rules, at least for this section. We will learn a few more rules. In particular, how do you multiply functions? What if you want to take the derivative of the product of two functions, or if you divide two functions? So we'll do that in the next section. But there's more in this section, though. So I guess I'm going to erase this and start again. Okay. Yeah. So what else can we do besides the rules? Well, we're going to go back to the interpretation of the derivative. Okay. So in particular, oops, didn't need for that to happen. So, all right. Let me try that again. So here's an example. Suppose that s of t is equal to, let's do 2t cubed plus 5 times t squared. This is the position of some object, you could say some particle, some object, at time t. At time t. Oh, let's say t is in seconds. And let's say s, position, is in meters. Okay. All right. So, first question, let's find the average velocity from t is equal to, let's say, 1 second to t is equal to 4 seconds. Average velocity. Okay, so this you should already know how to do. This does not require calculus or derivatives at all, right? So when we talk about the average velocity, we're just talking about how far we traveled, right? Well, it's distance in this case, but displacement, right? The difference in the positions divided by the difference in the time. Right? So in other words, it's the position at time t equals 4 seconds minus the position at time t equals 1 second, divided by 4 seconds minus 1 second. In other words, right, 3 seconds, right? And so what's s of 4? Well, I need a calculator for that. So s of 4 is going to be 2 times 4 cubed plus 5 times 4 squared. So 4 cubed is 64, times 2 is 128, plus 5 times 16 is 80. So 128 plus 80 is, I want to say, 208. So that's s of 4. Minus s of 1, I think we can do that in our heads, right? That's just 2 plus 5, which is 7. So 208 minus 7 for the numerator, and that's going to be in meters, right? So 201 divided by 3 meters per second. And I get 67. Turns out to be exactly 67 meters per second. Okay, so that's the average velocity, right? No calculus needed here. But for the next part, right, we want to find the velocity. Sorry, I'm being a little sloppy here. Find the velocity at time t is equal to 2 seconds. Okay. So is this average velocity? Well, notice we're only given one instant in time, 2 seconds, at that time. At that time, there's no time that has elapsed. So even though they don't say it, this is instantaneous velocity. Okay. So how do we find the instantaneous velocity at time t equals 2 seconds? Well, we first have to find the derivative of the position, right? So let's do that first. The derivative, and I almost forgot what s of t is. It's up here, right? 2t cubed plus 5t squared. Sorry, that's a 5, not an s. These are s's. I'll try to be careful. Okay, so what's the derivative of 2t cubed plus 5t squared? So we have to use the sum rule, the constant times function rule, and the power rule. Well, I'm going to do it all at once. So if you're going to do this step by step, you might want to pause the video, but 2 times 3 is 6, and then 3 minus 1 is 2. So 6t squared plus 10 times t. Okay. So this is what we use for our velocity function. So this will tell us the velocity at any given time. So now, plugging in t is equal to 2, we get 6 times 2 squared plus 10 times 2. So 6 times 4, 24, plus 20. We get 44 meters per second. So that is how fast we're going at that moment, at that time. Okay. So that's, so that's derivatives as instantaneous rates of change. In this case, the rate of change of the position is the velocity. Okay. Yeah, but then there's the other interpretation as the slope of the tangent line. So let's look at this example. Let's show that the graph of, let's say, the function f of x is equal to 5x minus 2 cosine of x has no horizontal tangent line. There's no horizontal tangent lines. Okay, so how do we do that? Well, how do we find the slope of a tangent line? To find the slope of the tangent line, right, we need to take the derivative, f prime of x, right? So let's do that now. We just have to take the derivative of 5x minus 2 cosine of x. And again, I'm going to do this in my head, right? The derivative of 5x is 5. Minus 2 times the derivative of cosine of x is negative sine of x. But a negative times a negative is positive, so this is 5 plus 2 sine of x. Okay. So, let me just rewrite it again. That is the derivative, which means, right, this is the slope of the tangent line to the graph at x. Okay. Well, so what do we have to do? We have to show that there's no horizontal tangent line. Well, if the tangent line is horizontal, what's its slope? Right? So a horizontal line, right, you know what that looks like, right? Looks like this. Has a slope of 0, right? Remember, slope is rise over run. It's all run. There's no rise. It's not going up or down at all. So 0 divided by anything is 0, right? Well, 0 divided by 0 is undefined, but 0 divided by 7 is just 0, right? So the slope is of a horizontal line is 0. So how do we know there's no horizontal tangent lines? Well, if this is the slope, let's see what happens. If we set this equal to 0, for what x does this become true? Right? In other words, if the slope is equal to 0, what values of x could that occur at? So we just have to solve this equation. Right? And this is a trigonometric equation. You should know how to solve those. Right? I mean, back in the day of your trigonometry classes, right? So first of all, let's just solve for sine of x. Let's take away the 5 from both sides. Again, that's a 5, not an s. So this is going to be 2 times the sine of x is equal to 0 minus 5 is negative 5. And then divide by 2. So we get that the sine of x, okay, that's an s, is equal to negative 5 divided by 2. So what angles have a sine value of negative 5 over 2? Yeah, I'm going to let you think about that for a second. Right? What angle, right? So remember, x is an angle here. Right? We can use theta if you want, but I'll stick with x. X is an angle in radians. Right. So you might think, well, to solve this, don't I have to take the inverse sine or arc sine? That's one way to think of it, sure. But what's the arc sine of negative 5 over 2? Of course, there isn't any. It's undefined. Right. So if you remember, for the sine function, the range of the sine function is between negative 1 and 1. Right. So negative 5 over 2 is negative 2.5. Negative 2.5 is less than negative 1. So yeah, sine of x does not equal negative 5 over 2 for any x. Right? In other words, this has no solution. Yep. Before I crossed it out, right? This equation has no solution, right? Which means the original equation, I erased it here, but this equals 0, right? That has no solution. Maybe I just better rewrite it, right? So the equation we originally wanted to solve here was 5 plus 2 sine x equals 0. Right? And this has no solution once and for all. Right? Which means that the derivative will never equal 0. Right? Which means the slope of the tangent line is never 0. Which means there is no horizontal tangent line. So no horizontal tangent line. Okay, that's just crazy sloppy here. Tangent line. No horizontal tangent line. Okay? And that was the original question. Show that there is no horizontal tangent line. So to do that, you take the derivative, set it equal to 0, solve for x, and, well, when you try to solve for x, you get no solution, or undefined, right? And that's how you know there's no horizontal tangent line. Okay, do I have time for one more? Well, okay, I'll make time for one more. And I'm not sure I have enough space, so let me clear this and start over again. Okay. All right. And so I think you'll see one like this in the homework. And I'm not sure I'm going to do the exact same one, but I'll do a similar one here. So here's the example. Right, so suppose f of x is equal to k times x squared. Okay, and we don't know what k is yet. In fact, that's the question. We want to find the value of k so that the graph of y equals kx squared is tangent to the line y equals 24x minus 36. Okay, so we're looking for k. Right? K is just a coefficient here, right? Right. So what is k going to be, right? Is it going to be 5x squared, 12x squared, negative 3x squared, right? What is this k here, right? Okay. Well, maybe before we tackle this, let's see if we can describe what's happening here, right? So let's graph the function. Now we really can't graph it here because we don't know what k is. But k is just a coefficient, right? So for different k's, you're going to get sort of different parabolas here, right? So this might be, this might be for k equals 1, right? And then this might be for k is equal to, 1/2. Right? It never says k has to be a whole number, right? K could be any number, right? Positive, negative, whatever, right? And then this one might be k is equal to, 7 or something like that. Okay. So we have different parabolas here for different values of k. But let's just pick one of them. Let's say it's this here, right? And now we have this line here is going to be a very steep line, right? The slope will be 24, and the y-intercept will be way down here, right? It's way down here. And so I'm going to exaggerate, of course, but if we draw that line, it should be tangent to the graph, right, at one of these points. I think I just missed, but let's say right here is where the line touches the graph. Okay. So what do we need? Well, we need to know where that point is. We need the x and the y, right? I mean, I guess we don't need them, but it would help to know where the parabola and the tangent line intersect. And I know they don't look like they intersect, right? So maybe let's do a slightly better job here. Just touching the graph here. Okay, that's a little better, right? At this point, x, y. Okay, so again, this green line here is this line, and then the yellow parabola is y is equal to kx squared, right? We want to know where they intersect. So to do that, we just take the y for the function, for the parabola, and set it equal to the y for the line. Right? So kx squared, this y here, is equal to this y over here. Great. Now just solve for x. Well, you can see we can't really do that here yet. There's a problem. This is one equation, but there's actually two variables. There's x and there's k. So this equation alone is not enough. We're not going to be able to find either x or k. So what else do we need? Well, what else do we know about the situation here? Right? Here's the key word. This green line right, is tangent to the graph at this point. Right. So if it's a tangent line, what else is true at this point here? What's true is that their derivatives are equal. The slope of the tangent line is the slope of the green line. Now, we could take the derivative of the green line here, but this is just y equals mx plus b. Right? So we should know that m is just the number in front of the x, right? So the slope of this green line here should just be 24. Of course, if you take the derivative of 24x minus 36, you get 24. So now what's the derivative of the parabola? Well, that you can do, right? K is a constant, and then the derivative of x squared is again 2x. And k times 2 is also 2 times k, so 2 times kx. Right? So that's the derivative of the parabola at any x. Right? At any x, but we're concerned particularly with just this one value of x, where the slope, the derivative, will be equal to 24, right? The same slope as the line. Right? That's what it means to be tangent. Okay, so now notice we have this equation here, and this equation is still not enough, right? This alone will not tell us what x is or what k is. So we need to use both of these, right? We have to solve this system of equations, right? So we have two equations in two variables, right? X and k. So the first equation is, well, I'll just rewrite it. Kx squared is equal to 24x minus 36. And if it's all the same to you, let me just divide both sides by 2. So you just get k times x is equal to 12. You can do that right away, right? So this is our system of two equations in two variables. And you should definitely try to solve this system yourself. Right? It is a nonlinear system. It is a nonlinear system because of the x squared here. But it's still doable, right? And when you're solving nonlinear systems, very often you want to use the method of substitution. So try to do that. Use the method of substitution to solve the system. And before you do that, though, remember this is a 24x minus 36, yeah? Okay, well, hopefully you got it. But let's do it, right? So remember, we're looking for k, so we can try to eliminate x. I can eliminate x by solving for x here. So I'm going to divide both sides by k here. Right? Cancel the k's. So x is really just 12 divided by k. Right? Now what I'm going to do is the substitution part. If this is equal to x, then this x and this x are both equal to 12 over k. Right? So in this equation here, again, that's a 4. Right? We're just going to plug in for x, 12 over k. So we get k times 12 over k squared is equal to 24 times 12 over k minus 36, right? There's no x here, so it's just negative 36. So we solve that equation, and we get, I think, 144 over k is equal to 24 times 12. I think that's 288 over k. Sorry, not equals, minus 36. Right. And I can subtract the 288k from both sides. 144 minus 288 is negative 144 over k, and that's equal to negative 36. So multiplying both sides by k, all right, I get negative 36 times k is equal to negative 144. I'll just switch sides here. and then divide by negative 36 on both sides. So k should equal, well, it's a negative divided by negative, so it's positive 144 divided by 36. I think we get k equals 4. And that should answer the question, right? Find k so that this situation happens. So k has to be 4. And we're done. Right. Now notice I never did, remember I said we have to find x and y. We have to find the point of intersection here. But we never did that. We can go back and do that now if we want, right? Now that we know that k is 4, right? What's x? Well, x is 12 over k. So 12 over 4 is just 3. And now what's y? Right? Well, y is 24x minus 36 on the one hand. Right? So this is going to be 24 times 3 minus 36. What is this? 72 minus 36, which I think is 36 on the one hand. But remember, it's the point of intersection. So if you used f of x is equal to kx squared, and by the way, k is now 4, so this is just 4x squared, and you plugged in x equals 3, again, that was the 3 we got from here, what do you get? You get 4 times 3 squared, that's 4 times 9, which is again 36, right? So the x and y up here, x and y up here are just 3 and 36. So x is 3, y is 36. So that's this point here on the graph. Not to scale, obviously. Okay. Again, that wasn't part of the question, but it could have been. It could say find the point of intersection, to find where the line crosses the, I shouldn't say cross, right? Where the line is tangent to the graph. And that's maybe a slight point here, right? If you have a curve like this and a tangent line, I would be hard-pressed to say that the line crosses the graph. It doesn't really cross the graph here, does it? It intersects it, but it doesn't really cross it, right? Because when you think of a line crossing a graph, you think of something like this, right? Or like this. But a tangent line intersects the graph. It does touch the graph, but it doesn't go through it. It doesn't cross it. Right. Anyways, k is 4. That's the answer. And I hope that helps. So there's questions like this that are similar in the homework, where you have to find a certain k where the graph is tangent to some line, some given line. Okay. So that's it for this section.